Okay, so welcome back. Today we are going to finish chapter 17. There's actually two main topics that we want to discuss for today's lecture. One thing is called the electroplating, the other one is called the electrolysis. Okay, so this two is actually sort of like the inverse process of your galvanic cell. And then if you haven't done so, please actually go to the YouTube video and then just go through those lecture videos so you will know the details about these two processes. Okay, so here we're going to summarize the things that we're going to use to solve the questions. All right, so typically for this inverse of galvanic cell or the electrolysis cell, the structure of the cell will look actually very different. Okay, so typically, you don't have the salt bridge anymore, okay? So you actually put all your solution together, okay? Therefore, it will look like something like this. Okay, so you're going to have a cell where you have your containers, and then you're going to put your electrodes inside your solution, and then you connect to a big battery, okay? And then inside your solution, you put your cation and then the anion inside. Okay. So in this case, okay, the electron will coming out from your battery, okay, and it's going to go through your cathode, okay, where the cathode is going to attract the cations, goes into the electrodes and got reduced. Okay, so remember we always mention this G rock, right? So it still holds in this type of cells, okay? So the things going to happen on your cathode is going to gain electrons, undergo a reduction reactions, and then by itself can serve as an oxidant, okay? And then it always happen at cathode. Okay, so once electron goes here, okay, the cation will come to the surface of your cathode and got reduced. Okay, and so key concepts actually inside your electrolytic cell, your cation will move toward to your cathode and then got reduced. Okay, so things is actually a process about reductions, right? So the electron potential is going to be relevant will be your reduction potential. Okay, so once you have the cation move to the cathode inside your solution, okay, your anion, okay, will feel the electric field and move to your anode and then undergo an oxidation reaction to generate the electrons so you can actually get back to your battery. Okay, so again, at your anode, okay, you still have your LoRa, right? You lost electron, you undergo oxidation, and this happened at the anode. Okay, so with that being said, it also says the potential that's relevant here will be the oxidation potential. Okay, so those are the very fundamental things that we should have. Okay, and then talking about the um, electroplating is actually a problem that it's going to say, it's going to understand, okay, once you actually dumping that much electrons into your cathode, right? And then all your cations will be actually reduced and generate some reduced product, okay? And how much it generate is actually the center of our calculation, okay, for the electroplating concept, okay? The other part is actually for the electrolysis is that, okay, so inside your electrolytes, you can have either cation or anions, okay? You may have multiple different species of cation and anions, okay? So the question you're going to be asked is to understand, okay, which cation or which anion will be the first species that got electrolyzed, okay? So those are the things that we will need to understand, okay? And to address those questions, then you will really need to know and compare the reduction and the oxidation potentials of different species. Okay, so those are the big pictures about today's lectures. Okay, and calculation-wise, let's talk about the electroplating first. Okay, so again, okay, the LoRa and G-Rock, okay, they're always true. Okay, for chapter 17. Okay, and then for the electroplatins, okay, the cells have the same structure of an electrolysis cell, which we just discussed. What it is, okay. And then for your calculations, okay, the things that you need to know is actually, okay, how much current or how much electrons that you have actually provided, okay. And then the way you calculate it is actually you start from calculating how many climbers you actually bringing into your electrode, okay. And the way you calculate is actually the amp times the time, okay, in second. Okay, so this is actually the amp of your current, okay, and then this is actually the time in seconds. Okay, once you do that, you will know how many electrons you actually bring in into the your electrode. Okay, then you divide that much electrons by the Faraday constant, then you can actually know how many more of electrons that you can actually bring into your electrode. Okay, then the next thing is actually you will know, okay, to produce one mole of your product, how many moles of electron that you will need to have. Okay, so that's actually the step number 3. Once you know the mole of product you're going to generate, by simply multiply its molecular mass, then you can actually get how many grain of product is going to form on your electrode. Okay, so 4 steps is actually listed here. Okay, but here is actually the equation you probably want to actually memorize. Okay, so here I actually summarize all these 4 steps into one single equations. Okay, where the G product is actually the grain of products that's going to form on your electrode. Okay, and then it can be calculated by first compute the m times second. That's going to give you the total electrons that you can going to add into your electrode, right? And then by dividing in the Faraday constant F, okay, then this will give you the number of mole of electrons that you provide into your electrode. Then you divide by that whole term with your NET, which is actually the electron, number of mole of electron that is needed to reduce one mole of your product. Okay, once you get that many mole of product, by simply multiply the molar mass, you can get the grain of product you're going to form on the electrode. Okay, so it's basically actually recapture the 4 step I just mentioned previously, but this will be actually the ultimate equations that you want to actually memorize to solve this kind of problems. Okay, so let's go through one example so you feel you know exactly how to use those uh, equations. Okay, so the question you're going to have is something like this. Okay, so it asks how many Columbus are required to produce 10 grain of iron metals from the solution of aqueous iron 3 chloride. Use scientific notation E with 2 numbers after the decimal. Okay, so this section of questions that we are going to encounter. Okay, so to solve a question like this, then apparently is uh, asking you how many Columbus, right? So Columbus is actually the keywords that you know that we need to go. Okay, so this actually basically just plug into the equation, right? The equation that we have learned is actually the grain of product on your electrode can be calculated by the amp that you provide times second, okay, divided by the number of mole of electron you will need to produce one mole of your product, okay. times your Faraday constant times the molar mass of your product. Okay, so if you read through the questions that you know, the grain of product is actually 10 grain. Okay, 10 grain of iron, right? Okay, and then you also know the product that you have, you want to have is iron metal, right? So the molecular mass of your iron, okay, be careful here, okay, not FeCO3, okay? This is actually not the things you want to use, okay? You want to know the molar mass of your product, right? Product is actually your iron metal, okay? So if you check out the periodic table, you will know the molar mass of iron is 55.8 gram per mole. Okay, so this is actually a number that you should use, okay? And then the Faraday constant, F, okay, is simply equals to 9.6485 times 10 to the fourth power. Okay, so this is actually a constant that will be provided in your test. Okay, so now you have this, you have this, you have this. Okay, so Columbus is the things that you need to know the definition, right? It is basically the amp times second. That's actually how you calculate your Columbus. Therefore, this term is actually things you want to calculate. Okay, to calculate, the only thing that you don't know is actually this, right? NET, right? The number of mole of electrons you will need to have to produce 1 mole of the product. Okay, so here you want to actually start to analyze what is actually the species that can actually produce your product. Okay, so apparently in this case, it's iron 3 chloride, right? So FeCl3. Okay, this one eventually become your iron. Okay, and then you know the oxidative state here is actually specified here, right? The oxidation number of the iron is actually 3. And then eventually become metal iron, right? Therefore, the oxidation number is 0. Okay, so for this process, then you should be able to see that your NET is going to equals to 3. Okay, that means actually you know these things as well. Okay, so you can actually reorganize these equations, right? So we know the Columbus, okay, maybe we just don't, okay, so let's just plug in the numbers directly. Okay, so we know 10 gram is going to equals to, on the top, okay, m times second, that's actually your Columbus, okay. NET is equals to 3. Faraday constant is 9.6485 times 10 to the fourth power. Okay, molar mass is 55.8. Okay, so by solving this equation, you should be able to get your Columbus equals to 5.19 times 10 to the fourth power. Okay, so this will be how you actually solve for this problem. Okay. So this is actually the application of this specific electroplating equations. Okay, so you can go back home and try to solve question number 4 by yourself. Okay. Only thing you want to be careful is that here is actually hour. Okay, but you will need to actually use second to do all the calculation. All right, so let's actually the first topic that we want to actually go through today. Okay, so let's look at the more interesting part here. Okay, the electrolysis is actually the things that most students is going to get confused. Okay, so there are actually 3 type of questions you're going to encounter in this chapter. Okay, so inside your solution, okay, so inside your solution, okay, meaning right here. So if you can actually either have a molten salt or mixed molten salt, or you have aqueous solution. Okay, under each conditions, the consideration will be slightly different. Okay, the things that will still hold is that you should know that in your castle, okay, so G rock, okay, so at the castle, you're going to have your G rock, right? That means actually you're going to have a reduction reaction. Okay, and then here the things you want to consider is actually your E naught reduction, right? The reduction potential is the most important thing that you want to actually consider, right? Every time you see castle or every time you see the G rock, then looking for the reduction reaction, okay? And then if actually undergo a oxidation reaction, then we know you need to actually consider the things happen at the anode, right? So anode is actually undergo a oxidation reaction. Okay, and then here the things you need to consider is oxidation potential. All right, for the electrolysis, okay, if you have less negative either reduction potential or less negative oxidation potential, okay, and lead species will be the first species to be electrolyzed. Okay, so this is actually in fact the things that you will always need to use to make the judgment. Okay, so those are the general concepts. Okay, so let's talk about these three different cases specifically. Okay, if you have a simplest case where you only have a molten salt inside your solution, for example, you only have the molten Na plus and Cl minus. Okay, and then this is actually your cathode, let's say anode. Okay, so on your cathode, what's going to happen is actually the Na plus, okay, will be reduced, right? So Ka go to cathode means actually G rock, right? So Ka goes to your cathode got reduced, right? Therefore, the things that matters is actually your reduction potential. Okay, and then anion, okay, go to your anode, right? So go to anode, let's say actually your LoRa. Therefore, you will need to know the oxidation potential for the specific reaction. Okay, so put it into this example, then you know this is actually the reduction potential of your sodium, right? So sodium plus electron becomes sodium. Then you will need to know the reduction potential for that. Okay. For your LoRa, then you know it's actually your Cl minus is going to lose electrons, right? So Cl minus will become Cl2, and then to give you 2 electrons, right? And then here you will need to know the oxidation potential of this HAP reaction, okay? And then to make sure the electron are the same, right? So you multiply 2 here. So that when you write out the equations, you have actually a correct number of electrons that being consistent in both your LoRa and G-Rock. Okay. The things that will always be asked for this type of questions actually, you are going to ask you what is actually minimum voltage you need to actually apply so that you can make this reaction to occur. Okay, and the way you calculate that minimum voltage is simply the sum of these two HAP reaction. Okay, and I also want to emphasize that even though we multiply 2 here, okay, your reduction potential and oxidation potential, they are intensive property, okay? So despite you actually multiply any coefficient here, the value of this, they won't change, okay? So to calculate the minimum voltage you will need is simply, again, the sum of these two. All right. So that is actually the first and the simplest conditions that you are going to check. Okay. Second is the mixed mutant salt. Okay. So what it means is that inside your containers, okay, let's say you have sodium plus, okay, and then calcium 2 plus, okay, and then aluminum 3 plus, okay, so on and so forth with multiple different ionic species, okay. You may have Cl minus, SO4 2 minus, PO4 3 minus, okay. And then it's going to ask you, okay, among all these cation and anions, which one is actually the one that will be first got electrolyzed, okay, in your electrolysis cell. Okay, so if that is the case, then the way to make the judgment is that, okay, so this sentence actually summarizes the way you do it, okay? So if you look at your G-Rock, okay, look at your castle, okay, so the cation with less negative reduction potential will get reduced first, okay? And then for your LoRa, okay, the anion species with less negative oxidation potential will get oxidized first. Okay, so those are the most important concept that you should actually have for now. All right. So with that being said, let's go through a few examples so we can actually strengthen all this concept here. Okay, so if we look at question number 5, okay, so it says in the electrolysis of molten lithium bromide, which product forms at the anode? Okay, so a few keywords, right? Keywords actually electrolysis and then the anode. Okay, so anode is going to undergo the LoRa, right? So means actually things that you care about is going to happen at your anode. Okay, so since it's actually anode, then you know you're looking for the anion, right? So if you look at this, the mutant salt of lithium bromide means it's going to become lithium plus and then Br minus. Right. So things right now, you know, you're actually looking for the anode. Therefore, the things that's going to be relevant will be your anion, right? So the anion species that you're going to have is actually Br minus. Okay, therefore, you know your Br minus is going to undergo a oxidation reaction, right? Therefore, you know it's going to give out its electron. Okay, once it gives out electrons, this is actually what is going to happen, right? So this is therefore will be the product that's going to form at the anode. Okay, so if today we want to know what product is going to form at the cathode, okay, then we know since it's cathode, right? So it's actually G rock, right? Because there's actually your cathode. Okay, and then we know K ions go to your cathode, right? Therefore, the things you want to care is actually the lithium plus. It's undergo a reduction reaction, therefore getting 1 electrons. It's going to become lithium solid. Okay, so if they're asking the product at the cathode, then the product will be simply the lithium. Okay, so this is actually the simplest case, the simple mutant salt, right? Okay, so this is actually how you solve a question like this. All right, so that is actually the first questions that we want to go through. Okay. So if today if today I have different mutant salt mixed together, for example, if today I have AlCl3. Okay, so if that is actually another salt that we have inside my cells, okay, then things will become actually quite interesting because AlCl3 is going to become Al3 plus your Cl3 minus. Okay, so if you look at your anode, okay, which anion will be important, right? So you know, if that is the case, then you should also consider 2Cl minus. They become Cl2 plus 2 electrons. Okay, so in this case, you want to actually consider the oxidation potential of your Br minus and then the Cl minus. Okay, so whoever is actually whoever is actually less negative, then less species will be the species that's going to be, in this case, oxidized first. Okay, and then for your anode, for your cathode, okay, for your cathode, then you should actually consider Al3 plus, gaining 3 electrons, they become Al solid. Okay, so here you want to actually consider the reduction potential of your lithium plus, and then the reduction potential of your aluminum 3 plus. Okay, you want to actually looking for the one that is actually less negative, okay, and less species will be the species or the product forms at the cathode first. Okay, so this is actually a simple example, so you can actually see how to predict who is going to form at the anode or the cathode. Okay. The most confusing questions that in this chapter is actually the tab number 3, okay, which we want to talk about here again. Okay, so if today you have a aqueous salt solution, okay, so aqueous salt solution, okay, the keyword is aqueous, okay. If that is the case, then because right now you have water inside your solutions, okay, so you also need to consider the oxidation and reduction of water, okay. So these are the two equations that you need to actually memorize it. Okay, the first one is the H2O got reduced. Okay, you gain 2 electrons and produce H2 and 2OH minus. Okay, so since it's actually a reduction reactions, right? Therefore, you know it's actually a G-ROC for water, right? So you need to actually memorize what product is going to form. Okay, in this case, it's actually H2 and 2OH minus, and the typical reduction potential is negative 0.83. Okay. The other one is actually your LoRa. Okay, so in this case, the product will become O2 and then 4H plus. Okay, and then the oxidation potential is negative 1.23 volt for water. Okay, so every time when you see this reduction potential and oxidation potential, it always refers to the species on your reactant side. Okay, so make sure you know that minus 0.83 volt is the species of your H2O. Okay, undergo a reduction reaction. Okay, minus 1.23 will be the oxidation potential of your H2O. Okay, so those are the things that we should have in mind. Then we can actually start to go through a few examples and then learn how to actually solve these problems. Okay, so in this specific question, it says the hydrogen can be prepared by suitable electrolysis of aqueous rubidium salt. Okay, so the things like keywords, okay, is hydrogen. Okay, that is actually things that you want to see. Electrolysis is actually the process, right? And then the salt you have is actually aqueous rubidium salt. Okay, that's actually a lot of information here. Okay, so this apparently is actually electrolysis questions, right? And then we want to know, can the hydrogen be produced by electrolysis with water, right? So hydrogen apparently is actually the reduction product of your water, right? Because we just say, okay, in the G-rock, okay, what's going to happen is that your H2O, okay, 2H2O plus 2 electrons is going to give you H2 plus 2OH minus. Okay, so this is actually a reduction reaction, right? So you want to also remember that for water, the reduction potential is actually 0.83 volt. Okay, so what it means actually, if you apply your voltage to 0.83 volt, then if you only have water inside your container, then you're going to be able to produce H2, right? So right now the problem is that, okay, besides H2O, you also have a salt, okay, which is actually a rubidium salt. Okay. It's going to be at the G-rock, right? So then it's going to be reduced as well, right? Since it's G-rock, then the species that matters is actually your rubidium, right? So then you want to actually know rubidium is actually 1A group member, right? So if you check out your table, right? So the reduction of your rubidium plus, okay, which is going to be B solid. Okay, so if you check out this, okay, and then the reduction potential of this species is negative 2.98 volt. Okay, so apparently rubidium actually need you to actually turn on your battery to 2.98 volt so that you will produce this solid, right? And then this is going to be achieved first. Therefore, you'll be able to produce H2, even though you actually you undergo electrolysis of a rubidium salt aqueous solution. Okay, so since that is the case, so the answer will be yes, even though you are actually undergo electrolysis of aqueous rubidium salt solution, but since the hydrogen can be produced at a lower voltage, therefore you know the hydrogen will be produced. Okay, so this is how you solve question number 6. Okay, let's look at another example. Okay. Number 7 say the oxygen can be prepared by suitable electrolysis of aqueous perchlorate salt. Okay, so it says oxygen, right? So apparently oxygen is actually the oxidation product of your water, right? So therefore you know the things that matters, okay? LoRa, right? So the things that matter is actually your anion, right? Okay, so for the LoRa of water, okay, the equations that you should use is that 2H2O that becoming O2 plus 4H plus 4 electrons. And then the oxidation potential is going to equal to negative 1.23 volt. Okay. So once you do this, okay, as long as the other ionic species inside your solution, if those oxidation potential is actually more negative than this value, then effectively you will just electrolysis your water, right, and produce your O2. Okay. Then we want to actually know what is actually the ionic species that you have, right? So here, you have actually a perchlorate anion, right, which is actually ClO4 minus. Okay, so these anions, okay, if you check out the oxidation, the reduction potentials, you probably won't be you won't be able to find it of this species in the product side on your table. Okay, so previous talk about this so-called the complex anion. Okay, we previously talked about a few example. For example, NO3 minus, SO4 2 minus, PO4 3 minus. Okay, all the things is actually so-called the complex anion. Okay, so all these anions, they're actually extremely stable. Okay, so if you want them to actually undergo oxidation or undergo reduction, it actually typically don't do that. Okay, so if you check out, okay, if in fact, if you want to actually find out the oxidation potential of ClO4 minus, you can actually find it. Okay, we just don't have the value. Okay, it is very difficult to further oxidize this species. Okay, so with that being said, okay, so the ClO4 minus, okay, if you want it to further donate electrons, okay, this is actually undetectable. Okay, it means actually it's going to be extremely big. Okay, so these things won't happen. Okay, therefore you know this will be actually the only reactions that's going to happen at your anode. Okay, so since that is the case, therefore you can say yes, the O2 will form at the anode. Okay, so that's actually how you solve question number 7. All right. So let's look at another example question number 8. Okay. So it asks you what products forms at the cathode in the electrolysis of an aqueous solution of this salt. Okay, so again, the things we care about is cathode, right? So the things that matter will be the kaons, okay, and then it will be a reduction reaction, right? So GROC. Okay, so it's reduction reaction. Therefore, the things you want to consider is actually your E-nut reduction. Okay. So kaons, okay, apparently for your salts, okay, the cation will be your K plus, right? The potassium. Okay, so the potassium, you want to know the reduction potential, right? So potassium plus 1 electron, they become potassium solid. The reduction potential, if you check out the table, you're going to find a value of minus 2.92 volt. Okay. And then another important thing here is actually you have aqueous solutions, right? So for the aqueous solution on the cathode, then we know it's undergo a reduction, right? So the reduction potential of your water, okay, it's going to generate the H2 plus 2OH minus, right? We know the reduction potential of your water is simply equals to negative 0.83 volt. Okay, so if you compare the reduction potential between the two, right? Apparently, the water has less negative value, right? Therefore, this will be the reactions that's going to happen undergo the electrolysis. Okay, and then once these things happen, the product that's going to form will be your H2 and OH minus will form on the castle. Okay, So this is actually how you solve this problem. Okay, but you can actually ask the same questions, right? What product forms at the anode? Okay, if you electrolysis this, again, the same salt as for example, okay? So if today you do the anode, okay, therefore you know the things that matter is actually anion, right? And then the reaction that matters is actually your LoRa, which you want to check out the oxidation potential, right? So E naught oxidation potential. Okay, the anion you're going to have here is actually PO43 minus, right? So this is the complex anion, right? So basically you can actually ignore the presence of that. Okay. But since actually right now you have water, right? So if water at the anode on the LoRa, then you know you're going to oxidize um, your H2O, right? So what you're going to have, the reaction you're going to have is actually 2 H2O undergo oxidation. They produce O2 plus 4H plus 4 electrons. Okay, and then the E naught oxidation will equals to negative 1.23 volt. Okay, so if you do the things, the same reactions, and then the product is going to form at the anode, oh sorry, yeah, at the anode will be your O2 and then the H plus. Okay, so hopefully it actually like makes sense to you, and then hopefully you actually understand how to use these simple principles to actually calculate, to actually predict which species that's going to form at the cathode and the anode. All right. So this will actually conclude the things that we want to learn for chapter 17. But before we finish this, I want to actually go back to the question number 1 that I went through previously, because I just realized that some of the numbers is actually not correct. Okay. So previously we say if you compute these values, okay, and then you are going to get, okay, let me erase this. So if you compute these values, then you are going to get the natural log k is going to equals to 0.7788. Okay, once you have that, then you can actually compute your k by take the exponential on both sides. And then by doing that, you will be able to get a value of 2.179. Okay, so this will be the correct answer for these specific questions. Okay, so previously I provide a k, the answer is 3.4 times 10 to the negative 1. So this is actually an incorrect answer. Okay, so please correct this answer into 2.179. All right, so with all this being said, I think they conclude today's lectures. Okay, so we're going to move to chapter 18 next time then. Okay, I'll see you next time. Bye now.